Hello, my name is Jack Handler, and I am from New York, America. At present, working in the village generally of India under my friend's YouTube channel FFBMD. FFBMD. Now, the today's topics in today's lecture, we will see about the phenomenon refraction of light. So let's discuss this phenomenon. When light goes from one media to another media, it bends from its original path, and this phenomenon is called refraction. That is the direction of propagation of light change moving from one medium to the another medium. In the case of refraction of light, some points are to be noted. The incident ray, refracted ray, and normal always lie in the same plane. The frequency and hence color and phase do not change going from one medium to another medium, while wavelength and velocity of light change when it goes from one medium to another medium. Refractive index of first medium multiplied by incidence angle is equal to the refractive index of second medium multiplied by angle of refraction, and this is called Snell's law, that is in formula form mu1 sin I equals to mu2 sin R, where mu1 and mu2 are the refractive index of first medium and second medium respectively, and I represent angle of incidence and R represent angle of refraction. This law is also known as Snell's law. Now some point according to based on Snell's law. If light is incident normally on a boundary, that is angle of incidence is equal to 0, then from Snell's law mu1 sin 0 equals to mu2 sin R, and this gives sin R equals to 0 or angle of refraction equals to 0. Thus it represents that light in the second medium will pass undeviated from the boundary, and so boundary will be invisible. Second point, if the refractive indices of two media are equal, that is if mu1 equals to mu2 equals to mu, say Snell's law implies that mu sin I equals to mu sin R. That is cone I equals to cone, that is angle I equals to angle R. That is ray passes undeviated from the boundary with cone I, angle I equals to angle R, which is not equal to 0, and boundary will not be visible. In this case also boundary will be not visible. Due to this reason, a transparent solid is invisible in a liquid if refractive index of solid is equal to the refractive index of liquid. Now we will see the some important points related to refractive index. Refractive index, it is represented by mu or a small n. First we see the definition of absolute refractive index. It is the ratio of speed of light in free space to that in a given medium, that is mu or n equals to a speed of light in free space by or divided by a speed of light in given medium, or mu equals to c by v. Now some important point related to refractive index. Refractive index is a scalar quantity and it has no unit and dimensions. If epsilon naught and mu naught are electric permittivity and magnetic permeability of free space, and while epsilon or mu of a given medium, according to electromagnetic theory of wave, C equals to 1 by under root epsilon naught mu naught and V equals to 1 by under root epsilon mu. And from this we get refractive index n equals to C by V equals to under root mu epsilon divided by mu naught epsilon naught equals to under root epsilon r by under root epsilon r into mu r, where epsilon r represents relative permeability of the medium and mu r represent relative refractive index of the medium. Next point, in a vacuum or in a free space, a speed of light of all wavelength is maximum and equal to c. So for all wavelength, the refractive index of free space is minimum, and mu equals to c by v equals to c by c equals to 1. Next point, that is refractive index of air or free space is equal to 1. For a given light, denser the medium, lesser will be the speed of light, and so greater will be the refractive index of that medium. For example, velocity in glass is less than velocity in water because water is optically denser than glass, and so refractive index of glass will be greater than refractive index of water. From this it is clear that in denser medium velocity is lesser, For a given light, refractive index depends on nature of medium, that is mu proportional to 1 by V. For a given medium other than free space, the speed of light of different wavelength is different. From it, it is clear that V proportional to lambda, directly proportional to lambda, and we have mu equal to C by V. So mu proportional to 1 by lambda, that is refractive index is inversely proportional to lambda, wavelength of light. That is, greater the wavelength of light, lesser will be the refractive index. So wavelength of red light is greater than wavelength of blue light, and due to this, refractive index of red light will be lesser than refractive index of blue light, that is mu r less than mu e, where mu r and mu e represent refractive index of red and blue light respectively. For a given medium other than free space, refractive index depends on wavelength of light, that is mu proportional to 1 by light, 1 by lambda. In the case of light in free space, C equals to f lambda naught, where f is the frequency, and in a medium V equals to f lambda, hence mu equals to C by V equals to lambda naught by lambda. That is, for a given light and medium, refractive index is equal to the ratio of wavelength of light in free space to that in the medium. Now we will go to know about relative refractive index. When light goes from one medium to the another medium, the refractive index of second medium relative to first medium is written as mu 1 mu 2 and is defined as mu 2 1 equals to mu 2 by mu 1 C by V2 by C by V1 equals to V1 by V2. While using the concept of relative mu, it must be noted that 2 mu 1 2 mu 1 is equal to mu 1 by mu 2, and 1 mu 1 to mu 2 is equal to mu 2 by mu 1. So 2 mu 1 is V2 equals to V2 by V1. Now 1 mu 2 multiplied by 2 mu 1 equals to V1 by V2 into V2 by V1 equals to 1. So we can write 1 mu 2 equals to 1 by 2 mu 1. Generally, mu is used for relative refractive index, and it implies the refractive index of denser medium relative to rare one. That is, mu equals to mu d by mu r, where mu d represents reflective index of denser medium and mu r represents refractive index of rarer medium. Now, according to Snell's law, mu1 sin I equals to mu2 sin r. The refractive index of medium 2 relative to 1 will be given by 1 mu 2 equals to mu 2 by mu 1 equals to sin I by sin R. Next point, mu varies with lambda according to Cauchy relation mu equals to A plus B by lambda square plus dash dash dash, where A and B are constant.